Hello, my name is Jason Young, and I'm doing a summer internship with Dr. Vincent Knight on understanding the effect of individual behavior in hierarchical queues. Today I'm going to talk about selfish behavior in queues, a couple of models that I've built over the summer, and to conclude we'll talk about some further work. So what do I mean by selfish behavior in queues? Well, we're going to look at a small example. It's very similar to one that I've previously uploaded, but we're going to go over it again here for the sake of completeness. So here we have three players, each with their own properties. You can see the arrival time and the service time, which has an average of 1. The value and time of ice cream, which is basically how long a player will expect to wait for ice cream. And yes, so with that, our first player arrives at the system. He sees no one in the system. His expected cost is simply his service time. So as it's less than 2.1, he enters the system. The second player arrives, sees one person in front of him, so his expected cost is the person in front of him's expected cost plus his own, as he has no idea how long the person in front of him has been in the system. So he enters the queue. And when the third person arrives, there's two people in front of him, and as that gives him an expected cost of 2 plus 1, which is 3, he leaves the system as it's greater than 2.1. Now we can take a look at some summary statistics for this queue. And here we can see the cost per player. First player's cost is simply his service time. The second player's cost is his service time plus his weight, giving him a cost of 2.35. And the final player's cost is simply his skip cost. So this gives an average cost per player of 1.75. So that was selfish behavior, where each player is attempting to reduce their own cost with no thought to the system. So if we have a look at the same system but under social conditions, which means there is a central control attempting to reduce average cost per player. So we have the same three players, same properties for all of them, except now we have a policy, which means we are no longer interested in the player's opinion and that they do exactly as we tell them. This number of people is how many people are in the queue before they should skip. So the first person arrives, sees there's no one in the queue, he simply joins. Second person arrives, he sees there's one person in the queue, our policy now tells him to skip, as does the third person. So if we look at the summary statistics for this same system under those conditions, you can see the second player's cost has been reduced, and this leads to a reduction in the average cost per player. So what we're mainly interested in is the measure of inefficiency, or the price of anarchy, which is the ratio of the cost under selfish conditions to the cost under social conditions. And in our case, it's 1.036. We can quickly look at some past work by Dr. Vincent Knight and Professor Paul Harper, who identified some service and demand nodes using elective knee surgery, where patients could choose their service node based on waiting lists. So from here we can see a very classic demand graph, which simply, when it increases, it's when the people are skipping under social conditions but not selfish conditions, and it begins to decrease when they are skipping under both conditions. Everyone skips basically. So as we can see, as we increase the value of service in time, this peak rises up. So this is what I've been tasked to do over this summer. What all my work's been based on is this model, where players arrive at a constant rate lambda. They then enter a decision node and make either a skip or a join decision. If they join, they have a probability pi of leaving the system. If they skip, they are simply charged the skip cost of that station beta I. Each station has a service rate mu I, mu I, with number of servers ci. So we're going to look at the simulation model in a bit more depth. What happens here is after the simulation starts, we initialize the variables, which is storing the inputs, calculating the selfish policy, and then our first player arrives. After that, the clock increments and we find the decision maker at this new time. When we found the decision maker, they make either a join or a skip decision. Now if they make a skip decision, because we've assumed that skipping takes no time whatsoever, they simply make another decision to prevent redundant cycles of the model. However, if they make a join decision, they enter the station and the queue is simulated. What happens then is we check if the simulation time has elapsed. If no, we simply loop around the process. If it has, we end the simulation there. Let's have a look at an example using the GUI that I built here. We have all the parameters already entered. This is the inter-arrival rate or demand, the service rate or the service time, number of servers at each station, the skip cost, and here we have the simulation time and warm-up time. You can see, because this is a list of two numbers, that we have two stations here. So if we run this under selfish conditions, see what we get. We can see here we have a selfish policy of 1 and 30. What's happening at the first queue is a lot of people are already skipping, I mean almost all of them are, so there's no point reducing that policy. And at the moment that policy is 1, so not much point there, but there's not a lot of people skipping at the first station. So if we reduce the policy there, we should be able to reduce this average cost to 3.306. So if we keep the policy for the first station the same, and reduce this to 10, we should be able to get something. So the more decisions people make, the slower the model goes, and increasing the demand all the time drastically increases those decisions. And see with a reduced policy, more people have skipped the first station, which gives us a lower cost of 1.85. So we've talked about selfish and social policies. But how do we find the best social policy? We chose to use a number of heuristic methods. The first one is a smart search algorithm, which finds the selfish policy and searches in a range around that. For every range, we run the simulation model 10 or so times, so it becomes very computationally heavy. After 10 or so times, it increases the range around it until it finds a better policy, one with lower average cost per play. Once it finds that, heuristic resets the search range around the new policy. We've also got a very, very early thing I made, which is just a random, it picks policies randomly and then finds one it likes, which has a lower average cost per player. So this is the effect of our very smart search algorithm, which took me about 3 days to program, and this is something that I did on day 4. It turns out that dumb luck beats clever coding. We talked about how it was computationally heavy, how this simulation model needs to be run a lot of times. So what we did, we turned to the Advanced Research and Computing at Cardiff, ARCA, and then Merlin supercomputer. You can see by the specs here, it's quite a nice piece of kit. So why did we choose to use a supercomputer? Mainly because we needed to run a lot of trials. These trials are embarrassingly parallel, which basically means we need to run a lot of identical things very quickly. Using aspect of Python multiprocessing, I managed to parallelize the code, and we were running it on 8 cores of Merlin. With that, running it 24/7 used 86,000 computing hours. What we were running on Merlin mostly was this case study about referral rates from general practitioners to the A&E. So here we can see they arrive into the system with Lambda, they arrive at their decision node, and they can either join the GP, which has a service rate of 12.5 patients a day and 5 docs available. People are willing to wait 2 days to see their general practitioner, but if they go see their general practitioner, 80% of them leave the system, so only 20% of them actually go to the A&E. In the A&E, we've assumed that there's 2 doctors on staff to take the patients from this general practitioner, and they work at 2 people per hour or 48 a day. People are willing to wait 8 hours a day, 8 hours, to see the A&E. This is a price of anarchy against demand graph, and it has this very similar shape, where selfish people are social people are skipping, but selfish are not, and then everyone begins to skip, and price of anarchy is reduced. Once we actually began using the simulation model, we realized we could solve this problem analytically. So we came up with some formulas. This here is an iterative formula for the arrival rate at each station. This here is a formula for the cost at each station using the MMCK queuing probabilities, pi n and pi j. Then we take a ratio of the arrival rate at each station and the arrival rate into the system and sum that to get the total cost per player. So our big assumption here, mainly from here, is are these distributions Markovian? Well, we weren't sure, so what we did, we took the simulation data and we graphed that. The distribution graph of that looks like this, which looks negatively exponential. And now if we overlay the analytical results onto the simulation results, you can see quite a nice fit. It's very, very close. Let's look at a variety of values in time of services. See, this peak here is where we change the value in time of the service at the first station. And you can see increasing the value increases the skip cost. But at this point we started to get a little bit worried that we weren't seeing any variation, or these simulation graphs looked very similar. We were expecting a dual peak, and what was happening was it was hiding. Mainly that either with two servers the peak was too small to notice because the service time value of service was too small, or with one server the dropout probability was reducing demand and we weren't getting that peak, and once everyone was skipping and the dropout probability no longer mattered, we'd already gone past the point where everyone was skipping selfishly. Let's look at something rather similar, which is the effective service rate at the first station. As you can see, it's a very similar shape. Why that is, it's the traffic intensity that affects the location of the peak, which is a ratio of the arrival rate to the service rate. And so what we can say is that an increase in service time, increase in service rate is equivalent to a decrease in demand. So this is the first station, and if we change that to the second station, you can see the green and grey graphs from our previous slide model the fuel peak a lot more clearly. You can see that there. This is the effect of increasing the value of service at the first station. And not much interesting is happening below this red line, but this red line is just before the traffic intensity becomes 1. And we can see that as the value of service in time increases, the price of anarchy decreases. But these two lines here where the traffic intensity is above 1, so as we increase the skip cost, the price of anarchy is increasing. Now if you look at the same thing for the second station, a little hard to make out what's happening is as we increase demand, it's going up and then back down. The reason we went much higher was we wanted nice gradients like the first graph, so we pushed it until we got this blue line, which is at 160 demand with a slight curve on it. This next graph is quite interesting. This one shows that there is a point at which high referral rates reduce the negative impact choice has. We can see there is a referral rate at which the negative impact of choice is reduced. So you can see that this is the minimum. But if we increase the referral rate, see that the negative impact of choice is much, much worse. This is interesting because from a purely theoretical point of view, this is the point where choice has the least impact, but it may not be practical in our case study. Imagine a GP referring everyone it received to an A&E. So this is the second model I built over the summer, which is very similar to the first, except for one small detail where people can only make one decision. They can choose to join any queue they want, but only as soon as they enter the system. So here they have all the same properties as the previous queue. The main difference and the main problem with simulating this model was the policy. As we've seen before, the policy for the multi-decision case was simply a vector of length n. With this one, however, even with the two station cases we're about to see, you need a matrix of numbers where the columns correspond to the number of people in the second station and the rows correspond to the number of people in the first station. Each entry shows you where the player should skip to, which basically means if there's a 0, you should skip no stations, if there's a 1, you should skip one station, if there's a 2, you should skip both stations and exit the system. This policy has a very specific form of 0s in this corner here, 1s in this bottom left corner, 0s and 2s in this section here, and along the outside will be 2s, and those 2s carry on outwards, and these 1s carry on downwards. In fact, we will never reach any of those states, or even these ones. So, how do we know the policy will have this form? What we did is we created a little example to show you one of the states that can never happen. So this is our policy. Our queuing state is in 7-3. There are 7 people in the first station, 3 people in the second. So if somebody arrives and observes the system in this state, they enter the decision node, and our policy tells them to skip no queues and enter here. So now the queuing system is in 8-3. So when somebody arrives now, they are told to go by our policy to go to the second, skip both stations and exit the system. So far, this is completely fine. We can have this as we've just seen. Now what we can't have is a 1 below a 2. What that means is if we increase the number of people at the first station, like so, and somebody arrives here, what will happen is that instead of skipping both stations, you should now not skip the second station, which has not changed. So that doesn't really make sense. Now, here is the state we said could not happen, and also 2 others that are, by the same arguments, completely impossible. What we have here is that the right-hand boundary will always be made up of a wall of 2s, and the lower boundary will always be made up of a floor of 1s. So again, like the previous one, we have a number of random heuristics. This one is the dumb heuristic, which simply checks policy. This one doesn't have a low average cost, so it rejects it, finds one that does have a low average cost, keeps it, and then makes another random change. We made a rather big assumption here to do something slightly smarter, that the social policy will have the same form as the selfish policy. So this heuristic can only make changes based on the proof we've just seen. So along this diagonal here, it can make 2s, or it can change this 1 to a 2. What we then see is this will happen. Same thing, it'll reject it. If it finds one it likes, it will keep it and keep making more valid moves. Also, it opens up another valid move here, so it can keep on going. Now, if we keep on going, we can see that there's a small example here. This is from an actual simulation that we ran, and this is the selfish policy. If we look at the social policy of this, we can see that our smart heuristic has found this. Now, this is an extremely small example. The policies can be huge. I'll show you a contour graph now where you can't even see the line of 1s. Now let's take a look at the price of energy against demand. You can see here it's not a great graph. The numbers are jumping up and down over here. They eventually stabilize, but it's more or less straight here. The main point is the heuristics need more work. You don't find solutions quick enough. So let's take a look at that big policy I mentioned earlier. This is from our case study from the previous model. We can see that there's a huge area of 2s here and a huge area of 0s. To give some sense of scale, this tiny line here is that line of 1s. And if you look very, very carefully along this line, you can just about see the improvements the smart solvers made. I'll do that a few times. It's very difficult to see. But yeah, it's barely made a dent. We need to either run for a long time, or there needs to be a smarter way. So this is our first solver, the dumb random one, which has found this peak. It's not as high as the other ones, but we can see the same structure forming of a large peak around the same area. And now if we look at the smart solver, again, the peak's not that high, which means it didn't reduce the social cost as much, and hence the dumb luck beats clever coding. So in conclusion, we can say that higher traffic intensity increases the price of anarchy, or the measure of inefficiency. Along with this, selfish users will always make busier systems. Something interesting to note is hierarchical structure does not always contribute to inefficiency. Which basically means that just because queues are in series doesn't mean that we'll have these two peaks, as we saw before. The dropout probability can hide it. The peak cannot be big enough so it's masked in the other peak. Also good to note is the price of anarchy decreases over time, just because if you've got a bad system, one that cannot code, then choice does not have a negative impact. You cannot improve a bad system. Also, you can see that the peaks increased as with the value of service, and also that there is a dropout probability. Although it may not be practical, it does minimize the price of anarchy and impact of choice. So, in future, the main work to be done is all on the Balking Model, improving the approximation of costs for joining at the first queue. Also, we'd like to investigate the other ways of approaching it, such as Markov decision problems. Yeah, then that's that. That's what I've been doing this summer. If you've got any questions or comments, please leave them below. Thank you.
Sorry?
Are you okay?
Yeah, we're just fine. We're just fine.
This is the conference center.
Yeah.
We've got events coming in here today, so you guys can do it out here. Yeah.
Okay.
Okay, because we're with the conference that's tomorrow.
Oh, okay. Yeah, they're coming up to set up today.
Okay.
So are you part of, like, are you one of the exhibitors?
Yeah, well, I'm with the OR Society.
Oh, right, okay, cool. Yeah, they're doing it at like 4 o'clock then. Cool. Okay.
Yeah, we'll put everything back, don't worry. It's because you're dressed in shorts, they think you're just some hooligan.